Video, I'm going to give a brief introduction to the ATNF Pulsar catalog and some of the features that you might find useful for your own research and for Pulsar searching. So this is the ATNF Pulsar catalog, and this catalog contains information about all the pulsars that we currently know of, and that number is somewhere over 2,500 at this point. So it contains information about each pulsar, all the parameters we've measured, and as an aggregate, it contains information kind of by default about the entire pulsar population. So it's an incredibly useful resource for querying all sorts of information that you might be interested in learning about pulsars. So right off the bat, we can just go ahead and make a table of all the pulsars. So here they are, sorted by their name. And if I just go ahead and scroll all the way down to the bottom, you can see that currently in version 1.56 of the ATNF catalog, we know of 2,613 pulsars. And this table gives us information by default about all of their names, their spin frequencies in hertz, and their dispersion measures in parsecs per centimeter cubed. And you'll notice in some cases values don't exist, and by default that is just represented with an asterisk for values that haven't actually been measured. So there are columns with the different values. The columns next to the ones that have been measured, like for instance spin frequency, this number is the uncertainty in the last digit of the value that's shown in the previous column. So this 1 means 8.668247824 plus or minus 0.0000000001, and so forth for all of these values. Okay, so we might want to see more information in a table like this. So I'm going to go back and I'm going to select some other values. So I'm going to keep name. I'm going to go with position parameters like right ascension and declination. I'm going to pick up spin period, P0, and period derivative. That's the change in period over time, or sometimes we call this the spin down rate. I'll pick up DM, and I think with that set, I'll go ahead and make another table. Okay, so here you can see there are quite a few more values, but once again, if I scroll all the way down, I still have 2,613 pulsars. I just have more information per pulsar. Okay, so next I'm just going to pick a pulsar seemingly by random. So I'm going to go for 1631 minus 1612. Let's see, 1631 minus 1612. Here it is. So here's some information, the right ascension declination. You'll notice the name is just the first 4 numbers in the right ascension and the first 4 numbers in the declination. We have the spin period, 0.6 seconds. We have spin down, dispersion measure, and so forth. You'll notice next to all these values, there's this string of characters and numbers, RSM plus 13. If I click on that, that actually gives me reference information about the paper where all those values were published. For the name, that's telling you the paper in which the pulsar was published, first published, so discovered. And for all the other values, that's the most recent paper showing the most recent best value for, say, the spin period or the dispersion measure. So this pulsar comes from RSM plus 13, which is the Pulsar Search Collaboratory discovery and timing of 5 new pulsars. This is the first paper published in the Astrophysical Journal by the PSC, detailing those first 5 discoveries. And you can see a bunch of high school co-authors on that paper, 62 in all. Okay, so that's cool. That's the first PSC discovery. Now what about the first pulsar discovery? So I'm going to go back here and go down a bit, and you'll notice there's this sort on field. And so far I've been sorting by JName, but I could also pick up this parameter, date. You'll notice all these parameters to our links, so you can click on the link, and here, date, date of discovery publication. So I'll go back and sort on date. I don't think this is case sensitive. Sending date, fine. Okay, and there are these buttons down at the bottom too, so I'll make another table. Okay, so now you'll notice that the Pulsar names are kind of all out of, well, actually they're in order here, so they're in order per year, but you'll notice all the references are from, in this case, 1968. So since all these papers from 1968 have been sorted by Pulsar name, the first Pulsar discovered doesn't show up first, actually, but the first Pulsar discovery is right here, B1919 plus 21, published in HBP plus 68. So what is that? HBP plus 68, right here, Hewish, Bell, Pilkington. So this is Jocelyn Bell and her PhD advisor, Anthony Hewish. And this is the first paper publishing the discovery of pulsars. Okay, that's kind of cool. So all of this started about 50 years ago. And let's say we wanted more information, actually, about B1919 plus 21. So in that case, we could go to Pulsar names here, B1919 plus 21, and click on Get Ephemeris. Okay, so now what we're looking at is pretty much everything we know based on our pulsar timing experiments about this pulsar, having studied it for the past 50 years. And we can actually pretty well describe what's going on in the system with just a handful of parameters. You'll notice on top of some of the basic discovery parameters, we've measured proper motion. That's the change in rate ascension and the change in declination over time. We've measured spin down, F1, and also F2. So that's the second derivative of spin frequency. Okay, so that's actually a pretty straightforward timing solution, but we can look at some other ones. For instance, B1913 plus 16. Some of you may have heard of this one. So here you'll notice there's a lot more parameters, and that's because this pulsar is actually in a binary system. So its binary orbit is here, PB, and this orbit is in units days. So the orbit of this pulsar, it goes around its companion once every less than a day. In this case, it's once every 7 hours or so. This pulsar has a really relativistic orbit. So we measure binary parameters. We can even measure some general relativistic parameters because it's such a relativistic fast orbit system. And this pulsar was actually the first evidence, the first concrete evidence of the existence of gravitational waves. So by detecting the change in the orbital period, the decay of the orbit, this system pointed to basically the emission of gravitational wave radiation explaining this orbital decay. So that was pretty cool. What about some other ones? So J0737 minus 3039. Okay, so this is not in the catalog. Turns out I need to say A because this is actually part of a double pulsar system. So this is a pulsar orbiting another pulsar, and we denote these by J0737 minus 3039, A and B. And again, this is in a binary orbit, kind of by definition. You'll notice the orbital period is even shorter than the previous pulsar that I showed you. And this system provides some of the strongest tests of general relativity. Okay, how about J0337 plus 1715? Again, there are quite a few parameters here, and this is another pulsar that's in a binary system, although we still have some of the discovery parameters you'll recognize, like RA, DEC, dm, and some of the spin parameters. But in this one, notice it has an orbital period of 1.6 days, and it has a second orbital period of 327 days. And that's because this pulsar is actually in a triple system, so it's orbiting a white dwarf companion in the short orbit, and both of them are orbiting another white dwarf in a much longer, almost year-long timescale. So that's a really interesting system as well. Okay, finally, I just wanted to show 1909 minus 3744. Okay, so this is a millisecond pulsar, also in a binary system. So it has an orbital period of 1.5 days. But this is actually one of the millisecond pulsars in several pulsar timing arrays. So this is a very precisely measured millisecond pulsar being used for gravitational wave detection. And if you look at some of the parameters in this timing solution, they're measured to extreme precision. It turns out that the eccentricity of this system is quite low. So the orbit is almost perfectly circular. And the orbit of J1909 minus 3744 is about 45 times the size of the Earth and deviates from a perfect circle by less than the width of a red blood cell. So this sort of gives you an idea of the precision of the measurements that are made here, and also the wealth of information that's available in this catalog. Okay, so what if we wanted to, say, take a spot on the sky and see how many sources are around that spot? Well, we could just take a random position. So let's say an RA of 12 hours and a declination of, say, 45 degrees. And I want to look within a radius of that position of, let's say, 5 degrees. And I'll show the pulsar's distance from the center of this region. Okay, so I'll click table, and nothing shows up. So there's nothing we know of, no pulsars within 5 degrees of that position. What about 15 degrees? Okay, so there are 2 pulsars within 15 degrees of that random RA 12 hours, dec 45 degrees position. And they are both about 9 degrees away from that test position. Okay, so let's try a different position within 5 degrees, and I can change my coordinate system. So I can go to galactic coordinates. So this is galactic longitude and galactic latitude. So let's look at a galactic longitude of 0 and a latitude of 0. So this is looking towards galactic center on the plane and within 5 degrees. Okay, so there are tons. There's 132 pulsars within 5 degrees that we know of galactic center. So that gives you some idea about the pulsar density, but you can also use this tool if you've found a candidate and you want to see if there's a known candidate close by. Okay, so finally I'm going to take those same parameters, GL and GB, galactic longitude and latitude, and you can also plot some of the information in this catalog. So here I've made a plot. This is galactic longitude on the x-axis, galactic latitude on the y-axis. And galactic latitude goes between minus 90 and 90. And you can really see on this plot, similar to the query I just did within some position, a radius of some position, you can see the density of pulsars is quite high along the plane and highest near galactic center. Galactic longitude of 0, galactic latitude of 0. And it kind of falls off as you go away from the plane and away from galactic center. Okay, one more plot, and this might be one you're all familiar with. So I'm going to plot on the x-axis spin period, a log x-axis, and period derivative on the y-axis, also in log space. And this is what we call the PP dot diagram. So if I plot this, nothing happens. Okay, not really sure why. Well, I'm sure we will be looking at a PP dot diagram soon. Oh, there we go. Okay. I'm not sure why that didn't work. So here, this is probably a plot many of you are familiar with, or if not, you will probably be seeing it a lot soon. And the PP dot diagram is useful because it shows us sort of different pulsar populations. You have your youngest pulsars up in this region. As pulsars age, they move over in this direction, and this is the bulk of the pulsar population we know of, called normal pulsars, with spin periods around a second. And eventually they continue aging and cross what we think of as the death line, roughly here. And past that line, they stop emitting in the radio. You'll notice we have some high energy sources like magnetars, and also in the lower left of this plot, we have millisecond pulsars, which have spin periods of several milliseconds, and many of these are in binary systems, orbiting companions, and they get their fast spin periods through interactions with a companion that donated material and angular momentum spinning them up. So this gives us tons of information about the full pulsar population and pulsar evolution. And just getting back, that's a quick summary of the ATNF pulsar catalog and all the powerful things that you can do with it. But if you want to learn more, there's a slightly more in-depth catalog tutorial that you can go through on your own. And there's full documentation. So if you want to read about any other features of the catalog, you can go ahead and do that. Okay, I hope that was helpful, and happy searching.